through chapter 17 here. And we already talked about acid-base reactions. You know, we did metathesis, redox, and acid-base. Acid-base, there are different types of acid-base reactions. Proton transfer is one type, it's Bronsted. And then there's something called electron pair acceptor, electron pair donor, that's called Lewis. Lewis is the most comprehensive definition. And so all acid-base reactions are Lewis acid-base reactions, but Lewis acid-base, you know, it's kind of a broad definition, so it's harder to pick those up quickly. And so what we do is we subcategorize acid-base reactions into proton transfer, which are Bronsted, because these are a lot easier, and then the remaining we'll just call Lewis, because those don't fit this category here. And so we'll just look at Bronsted acid-base reactions. These are the learning objectives here. We'll skip those here and we'll just go straight to it. There's actually three definitions. There's Arrhenius, Lewis, and Bronsted. Arrhenius is the most narrowest of definitions, so people don't really use Arrhenius definition much. Arrhenius is anything that has H plus or gives H plus ions in water. And so usually when somebody thinks of Arrhenius acid, they just think of H plus. H plus is Arrhenius acid. That's it. Whereas Bronsted would say an acid is a proton donor, Arrhenius would just say an acid is H plus, AQ. And so there's only one reaction between Arrhenius acid and Arrhenius base. Arrhenius base would be hydroxide here. And so hydroxide in water, OH minus AQ. So Arrhenius base, H plus AQ, Arrhenius acid is H plus AQ, Arrhenius base is OH minus AQ, so H plus OH minus gives water, H2O. So it's Arrhenius acid-base reaction. So we're not going to spend that much time on Arrhenius acid bases. Primarily we're going to stick with Bronsted. Bronsted, even though it doesn't sound like it, it's a little bit more general as far as definition, because there doesn't have to be water present. Now, in the Bronsted acid, the acid is a proton donor, and the base is a proton acceptor. So the base doesn't have to have hydroxide, like ammonia. You know, ammonia is a base. There's no hydroxide in the ammonia itself. Well, if there's a lot of acid, we call it an acidic solution of a lot of acid in water. So there's more and more H plus. The more and more H plus we have in water, the more acidic it is. And the less H plus, the more basic it is. And there's a seesaw relationship between hydroxide and H plus. And there's an equilibrium that exists between hydroxide and H plus. So it seesaws one way or the other. And so the less H plus, that means the more hydroxide. The more H plus, the less hydroxide. So it seesaws back and forth. There's some coral that's in acid. Coral's mostly calcium carbonate. In fact, all carbonates are dissolved in acid like this. It doesn't matter the acid. They're attacked by acid that make H2O and CO2. Zinc reacting in acid, this is a single replacement. Zinc reacting with hydrochloric. It's not really an acid-base reaction, you know. And so, you know, when we think about acids we react with bases, but when we think about oxidizers react with metals. So acids, all acids are oxidizers as well because of the hydrogen ion being a decent oxidizer. So it's not an acid-base reaction. C, it's a redox reaction. Okay, so now we skip through Arrhenius. You don't really need to know Arrhenius, but you should know Bronsted Lowry acid base. Again, Arrhenius was just H plus. Base was OH minus, but if you look at this base, you know, this base doesn't have OH minus. So Bronsted is a little bit more broader as far as the definition goes. And so an acid is a compound which a proton can be removed. In other words, a proton donor. A proton can be removed. The language there is very interesting because normally when we think about an acid-base reaction, we think about the base plucking the hydrogen off the acid. And so this is why the language is, they don't say proton donor, but proton can be removed by the base. Base attacks this proton, flex it off. And when it flex it off, now this nitrogen has 4 hydrogens around it. Flex it off just as a proton, as H+. And so that leaves these electrons here. Normally we look at this mechanistically. And so the base is the compound that removes the proton. So an acid-base reaction is to transfer the proton. And so as far as how we visualize this reaction occurring, it's something like this. The base comes in and attacks here. So the base, we don't have to draw this 3D. But if we drew this 3D, what shape is this molecule, the ammonia molecule? That would be.
You mean like trigonal pyramidal? Or
Yeah, I mean trigonal pyramidal, that's the shape of it. And so if I wanted to be a little bit more accurate, I try to draw a trigonal pyramidal. Lewis structure is just kind of flat like this. So if I tried to be a little bit more accurate, what I do is I probably put the lone pair in the plane like this. And then one of the hydrogens here, that means one hydrogen sticks out like this and the other hydrogen sticks in like that, right? All right, now this nitrogen here is what we call delta minus because it's more electronegative than the hydrogens. And the hydrogens are all delta plus, like this. So delta minus is going to be attracted to positive charge. Well, if we look at a water molecule, water can be either an acid or a base. And so I'm going to draw the water like this. Maybe I'll draw, well, the way we draw it is we do 2 in the plane, and then 1 coming out, and 1 going in. This is for tetrahedron. The 2 in the plane will be at a 109 angle, like this. Water has a delta minus and a delta plus too. Both of these molecules are polar. And so it's just an electrical attraction. Well, basically, this lone pair here sees this and likes it, plucks that hydrogen off. And it plucks that hydrogen off, it leaves these bonding electrons behind. And so what we end up with is something that looks like this. There. Or now that nitrogen is going to have 4 hydrogens bonded to it in a tetrahedral arrangement. So what is the shape of this molecule? Well, it's not really a molecule, but it's an ion here because now this nitrogen has a charge of what? How many electrons does that nitrogen have when we're counting formal charges? You guys remember, this is from Lewis structure. When we do formal charge, how do we do it? Yeah, exactly. We have to do a 50-50 split. And so how many electrons does nitrogen end up with in this structure? 4. It's supposed to have how many valence electrons? 5. So it's short one. So this nitrogen short one. These are the types of things that become clearer after repetition. A lot of people say, oh, why go through it so many times? The same thing over and over. Sometimes you go through the same thing over and over, and then you start to see connections, or you start to see new things happen. And this is why, people pore over the data. Sometimes they don't see it, and then a new person pores over the data, and maybe it becomes obvious. But the more times you go through it, the higher the chance that you'll be able to make these kind of connections. And so one of the connections is this. You go through formal charge, we go through oxidation state, and we go through octet over and over again, and then pretty soon you can make a connection. Do you know what the connection between formal charge, oxidation state, and Lewis is? Well, basically, what up to now, we can summarize it like this. Up to now, hey, wait, there are 3 ways of counting electrons in a structure. 3 ways of counting electrons. If we count the octet/duet, then we're looking at the total. And so let's look at this ion here, ammonium ion, as an example. If we look at octet duet, everybody's happy because everybody has an octet or a duet. So the nitrogen, octet. How many electrons does nitrogen have? 2, 4, 6, 8, right? And so we count it. Hydrogens are happy because each hydrogen has a duet, 2 electrons to complete the first shell, 8 electrons to complete the second shell for nitrogen. And so that's the octet duet. This is 1. 2, oxidation state. What's the oxidation state of nitrogen and hydrogen? What's the oxidation state? Well, which one do you do first, nitrogen or hydrogen? Hydrogen. Hydrogen's going to be +1. Nitrogen is -3. +1 times 4 is +4, -3 is +1, which gives us a net charge. If you look at this, what this is equivalent to is this. Nitrogen ends up with 3 extra electrons. So nitrogen ends up with all the electrons. And hydrogen ends up with none. And so nitrogen takes all the electrons, and so we end up with a -3. And then each hydrogen ends up with no electrons, and so that ends up being +1. Oops. +1. And so for oxidation state here, if I were to summarize this, then we say that the bonds are 100% ionic bonds. And so we assume all bonds are 100% ionic. That is, winner takes all. This is what I call it, winner takes all. Who's the winner? The more electronegative atom. Winner takes all. Nitrogen takes all the electrons. Hydrogen's left with no electrons. And then finally, formal charge. Would be 3. In formal charge, we do, the same. We split the bonds. With formal charge, we split the bonds down the middle, such that one electron ends up with nitrogen, and the other electron ends up with hydrogen in all the bonds. So when we count the electrons, hydrogen has 1 electron, so the formal charge is 0. 0, 0. It ends up with 1 electron. Unfortunately, nitrogen only ends up with 4 electrons. It's supposed to have 5 electrons, and it ends up with a positive charge here. And so this is what we call covalent. And so we assume all bonds are 100% covalent. And so I call this 50-50. Everything's split in half. 50-50 sharing. what's the reality? Well, the reality is these bonds are polar covalent. So the reality is they're somewhere in between ionic and covalent. They're polar covalent. And well, we aren't going to get into the detail. We don't compare. The thing is, we never compare formal charges with oxidation states, because that would be like, that would be comparing, okay, what's the biggest apple? Well, the biggest orange is this. Well, I didn't ask about oranges. I asked about apples. So you don't compare these. What we do is we compare formal charges with formal charges, and we compare oxidation states with oxidation states. And when we compare them, then it's a fair comparison. But if we try to compare them like this, why does nitrogen have a -3 here and a +1 here? It's totally different charge. And the way you reconcile it is we don't compare these two numbers. They're used for different references, and they're used to predict different things as far as the properties go. There's a charge here. All these have a net positive. This is net positive here. -3 + 1 + 1 + 1 + 1 is +1. And +1 + 0 + 0 + 0 + 0 is +1. So all these have +1 net charge. Okay, and so we end up with a positive formal charge here. It ends up short 1 electron. And we're looking at the formal charges, and that will result in this charge here. And then what's going to happen is we're going to get this. Now we're going to put the 2 in the plane. So this lone pair and this bond are 109, and they're both in the plane. To show the lone pair in the plane, I've just drawn these little dots like this. And then one lone pair sticks out of the plane, so we'll make that bold like this. And then one lone pair goes in. And so what's the geometry of this here? Molecular geometry. Tetrahedral. What's the molecular geometry of this? It's linear. 2 atoms are always linear. But if we look at the electron geometry, it would be tetrahedral as well. So I tried to draw the tetrahedral here, but it's tilted because I have 2 in the plane, like here, 1 sticking out, 1 going in. So 1 sticking out, 1 going in, so it's just tilted. Okay, now we look at the charge. We're not looking at the oxidation state, we're looking at the formal charge. When we do Lewis structures, we always write the formal charges for the atoms that are non-zero. And so here, what are the formal charges?
Hydrogen's a 0 and then oxygen's a minus.
Yeah, oxygen's a minus, net negative. And then we add up the formal charges. -1 + 0 gives us minus. And so this would be an example of a Bronsted acid-base reaction. Here the base, base is like hydrogen. Here, the hydrogen has to be, polar. So for example, water is okay, but if I had something like methane, methane has 4 hydrogens on it, and so isn't methane a good acid? Would methane be considered a good acid? No, methane would not even be considered acidic. Why is that? I mean, it's got 4 hydrogens. And acids are hydrogen donors, right? Acids are hydrogen donors, and water only has 2 hydrogens, and methane has 4 hydrogens, so shouldn't methane be a better hydrogen donor than water? So why wouldn't ammonia be attracted to methane? In fact, it's not attracted to methane at all, because why? No need for hydrogen on methane? Well, Okay, if it had a choice, ammonia could attack water or ammonia could attack methane. Which would it have a preference? No preference?
It would prefer water.
It would prefer water. Why would it prefer water over methane? I mean, methane has 4 hydrogens. Water only has 2.
Because the bonds on methane, I think, are covalent, or at least water has more polar,
Okay.
so it's more attracted to the electronegative, or the negative part is more attracted to the positive part of the water.
Yeah. That's the reason why. These bonds we call non-polar covalent because the electronegativity difference is very small. You know, hydrogen and carbon are about the same. Hydrogen is very tricky as far as electronegativity goes because on the periodic table, fluorine is the most electronegative. But if you look at hydrogen, hydrogen is here and here, so hydrogen is kind of in the middle, right next to carbon and boron. In fact, it's between carbon and boron. And so the problem is yeah, carbon is just slightly. Carbon's a 2.5, hydrogen is a 2.1, and so it makes a very, very tiny delta plus. You know, so tiny we say it's kind of negligible, and we call it non-polar. You know, this is why hydrocarbons are non-polar. Water's polar. You know, and they don't mix. There's no charge polarization here, and so that delta plus is so small we often just ignore it, right? And so there's nothing to really attract the base to it, you know, because this base, this nitrogen's seeking not H, this nitrogen's seeking positive charge density. Well, it is also seeking H because it can pluck off an H and bond with it, but it would seek anything with positive charge. And so the reason why methane is because it's non-polar, and these bonds are highly polar. In fact, these bonds are so polar. You know, we say it's an unusually big dipole, right? Unusually big dipoles can lead to very strong intermolecular attractions called what? We had 3 levels of dipole. We had the London, we had the dipole, and we had the H bonding. So which one was the strongest? The hydrogen bonding. And so unusually big dipoles, which lead to hydrogen bonding. And so, yeah, this is unusually big dipole means big positive and negative charges. This is going to be attracted to this. Is non-polar. There's really no dipoles associated with that. And there are minor dipoles, and there's minor dipoles. But we're looking at bond dipoles here, not net molecular dipoles. Bronsted-Lowry acid-base theory. Okay, let's see what they're talking about here. I don't know. This is all theory. You know, this Lewis structure. This is all the theory of chemistry. So I don't think we need the theory on here. Bronsted acid-base. You know what amphoteric means? Water is what we call amphoteric. Yeah, it occurs on both sides of the acid-base chart. You know, amphoteric. I wish they had a fancy word for that for redox, you know. There's certain things can occur on both sides of the redox chart. You know, water occurs on both sides of the redox chart. Water can be both a reducer and an oxidizer. But there's no fancy word for it. Iron 2 is on both sides. Hydrogen peroxide is on both sides. So a lot of species that are on both sides of the redox chart. Water would be on both sides of the acid-base chart, but there are others too. Like bisulfate, bicarbonate, a whole bunch of species occur on both sides, and all those species are amphoteric. Now, water is very special as an amphoteric species because it doesn't care which way it goes. So water can go either way, acid or base. Whereas some species do have a preference. So for example, bisulfate much prefers to be the acid, and it's a very, very poor base. So poor that we don't really consider it much of a base. Hydroxide is amphoteric, you know, because it does have another hydrogen it could lose. You know, hydroxide, some this powerful acid can see that hydrogen and pluck it off. But you need a very powerful acid because hydroxide is considered a strong base in an acid. So you need a way stronger base than hydroxide to pluck that off. The super base. There are some super bases out there too that aren't necessarily on the list. There are super acids that aren't on our list because those are much more rare, highly reactive species. And so they aren't that common, so we don't put them on the list. When we do this, we have to look for driving force. So what is the driving force for an acid-base reaction?
Stronger acid to weaker acid.
Stronger acid to weaker acid. Now, the acid is always going to be the donor. And so this is the donor, so this is called the acid. And the acceptor is going to be the base. And so what we're doing is we're setting up a competition. Which side's more stable? The more stable side's going to win. The more stable side is going to be the weaker side. Weaker species are more stable. The stronger species are less stable. Stronger species being more reactive. And so what we do is we just set up a competition between both sides. Now, if we look at going backwards here, who's the proton donor? Who's the proton acceptor? Going backwards, which species loses the hydrogen? Which species gains the hydrogen? So if you look at this one, we start off with ammonium, NH4, and we end up with ammonia, NH3. So what happened? What happened was we lost a hydrogen. When we lose a hydrogen, then this must be the acid. Okay, and then over here we look at hydroxide. Hydroxide ends up converting to water, so we gained a hydrogen. So this is the base. And so we can make a comparison between the sides as a competition. Now, the other way of doing this is this. If this is the base, then the other side would be its conjugate. And so if that's the base, this must be the acid, conjugate acid. If that's the acid, this must be the conjugate base. So we do the conjugate pair. Okay, then we go to our acid chart. And then make a comparison. We probably don't need the acid chart for this one, but let me just show you again. We compare the two bases. Which one's a stronger base, ammonia or hydroxide? So here's hydroxide, here's ammonia. Which one's stronger?
Hydroxide.
Hydroxide is stronger. So this is saying we're going from a stronger base. Oops. Over here, this is stronger base, this is weaker base. So we're going from a weaker base to a stronger base. And then we look at water versus ammonium on the acid side. So water is here, it's a very weak acid. Here's ammonium, which is also a weak acid, but it's stronger. So this is a stronger acid. It's not a strong acid. It's a stronger acid than water. Everything's relative. And so here, is that driving force? Stronger species are more reactive or less reactive?
More reactive.
More reactive, and therefore less stable. So the driving force is reversed. So there's no driving force. If there's no driving force, then we expect no reaction, right? Stronger to weaker is a driving force. But it depends, you know, it's not so black and white because it is a competition. And so if you're going from something much stronger to something much weaker, or something much weaker to something much stronger. It depends on the difference in strength, because you have this competition. And so if you're looking at water and ammonium, if you're looking at water and HCl is way up there, right? And there's a huge difference in strength. Let's say on one side we have water, on the other side we have HCl. Huge difference in strength, which means a huge driving force, one way or the other. But if they're kind of close to each other, then there's not a huge difference. Let's say one is a little bit stronger than the other. If one's a little bit stronger than the other, then it's not so clear cut. It's not so black and white who the winner and who the loser is. Because if one is just slightly stronger, does that mean there's a clear-cut winner and a clear-cut loser? That means nothing happens? No. What happens is this. For this reaction, there's not a large difference in strength. It's still unfavorable. I should not say low, I should say huge. There's not a huge difference in strength. Still unfavorable. So we expect no reaction. But a tiny bit of reaction does occur. A tiny bit, less than 1% reaction does occur. So a little bit of ammonium and hydroxide do form. This has two important consequences. There are two important things that you need to be aware of that we talked about earlier. One, electrolyte properties. What we say is that bases hydrolyze. And so ammonia does not ionize. Ammonia hydrolyzes water. And so ammonia plus water forms ammonium and hydroxide. This is a weak base. Weak bases are weak electrolytes. So what happens here is that, it's a weak electrolyte, so it generates a small concentration of ions, which can conduct electricity. And so, we get a small concentration of ions generated. To show it's a small concentration, we draw two arrows. The arrow being in the reverse direction, much bigger, because that's the driving force. The driving force is in the reverse. Because if we go in the reverse direction, we're going from stronger to weaker. Bases hydrolyzed, small concentration of ions is generated. And important consequence number 2 of this is for metathesis. if a small concentration of ions is generated, then those ions can react. And so, a metathesis. With ammonia and ammonia derivatives. Ammonium-like molecules are called amines. But, that you don't have to worry about. There are lots of them. Lots of ammonium-like molecules that act in the same way. So if we have something like this, for example, magnesium chloride plus ammonia equals blank. This, we have to be aware, ammonia in water, this is ammonia H2, ammonia in water will generate some ions. And so we can treat this reaction, even though it's not a double replacement type metathesis reaction, we can treat this as a metathesis reaction. And so we treat this as metathesis. The way we treat it as metathesis is like this. We go magnesium chloride plus ammonia plus water. When we do ammonia plus water, what happens is there's going to be a little bit of hydrolysis because of this weak electrolyte. And so that's going to form ammonium and hydroxide, which we'll just call ammonium hydroxide. And so when we look at this, this is like a metathesis reaction. It's an AB plus CB. But we don't write ammonium hydroxide. We don't write ammonium hydroxide because, just a little bit's formed. But maybe it's enough, even though it's a little bit less than 1%, maybe that's enough to cause precipitation. And it is enough to cause precipitation for many, many cations. Not all of them, but many. Because it's going to be a small concentration of them. And so we treat ammonium in water as ammonium hydroxide. We can't buy ammonium hydroxide though. If you go to the store to buy ammonium hydroxide, you can't because ammonium and hydroxide will react. They'll react to form, ammonium and hydroxide will react to form ammonia and water, because that's favorable. That's going stronger to weaker. And so what forms in this particular reaction? What forms is, it would be an AB plus CD. So it would be magnesium with hydroxide. So magnesium with hydroxide, what's the formula for that? MgOH2. And then it'll be ammonium with chloride. What's the formula for that? It'll be just ammonium with chloride. They're both plus minus 1. And then we balance it. It looks like we're going to need 2 ammoniums and 2 hydroxides. For sure 2 hydroxides. So if we need 2 ammonium hydroxides, then we need 2 ammonias and 2 waters to balance it. And give us 2 ammonium chlorides here. Magnesium hydroxide is insoluble. Hydroxides are insoluble except for group 1 ammonium, calcium, strontium, barium, but magnesium turns out to be not one of the exceptions. It's tricky because calcium and strontium and barium hydroxides are soluble, magnesium hydroxide is insoluble, so it's weird. This is the H total, but this would be AQ. So again, ammonia ammonia is a weak base. It hydrolyzes water and creates ions, small concentration of ions. That small concentration of ions can participate in metathesis reaction. Yes. This is kind of an aside. And so this would be the complete equation. The ionic equation would look like what? Well, magnesium chloride, do we ionize that?
Yes.
Yes. those then to Mg2 plus 2Cl minus. Ammonia, do we ionize ammonia?
Yeah.
Yes.
No.
Or,
Ammonium hydroxide we would, but ammonium hydroxide we don't write there because ammonium hydroxide is not what it is. It's ammonia. We buy a bottle of ammonia and the ammonia reacts, a tiny fraction of it reacts with water to make that ammonium hydroxide. It is correct that ammonium hydroxide is what's doing the reaction, but when you're going to go buy the chemicals, you're going to buy ammonia, not ammonium hydroxide.
so in that case, even though it's aqueous, it wouldn't hydrolyze?
No, you only ionize the strong or hydrolyze the strong. And the strong bases, the strong acids, and the soluble salts. You leave everything else alone. Ammonia is a weak base, so we just leave it alone. Is water a strong acid? No. Is water a strong base? No. Is water a soluble salt? No. Leave it alone. Magnesium hydroxide, is that a strong acid? No. Is it a strong base? Is it a strong base? Aren't hydroxides strong bases? But it's insoluble. I talked about this at length. Do you remember when I talked about magnesium hydroxide? Milk of magnesia? You know, it's not a strong base. Is it a soluble salt? No, so leave it alone. Ammonium chloride, strong acid? No. Strong base? No. Soluble salt? Yes, all ammonium salts are soluble. So we ionize it. 2 ammoniums, 2 chloride. Okay, then we look for the spectators. Magnesium ions is for the net ion equation, are not spectators. Chlorides, yes, spectators. Ammonia. Ammonia is not a spectator because on one side we have ammonia, which is a base. On the other side we have ammonium, which is an acid. So it's not a spectator. 2 ammonias here. Water is not a spectator. 2 H2O liquids here. This goes to magnesium hydroxide, solid, and 2 ammoniums. So this would be the NIE. The driving force for this is precipitation. Magnesium hydroxide. And so again, this is a case where this base is acting in a metathesis reaction. But the first step of it, to generate the ions is a Bronsted acid-base reaction. So sometimes we have that. First step is Bronsted acid-base, followed by metathesis. Favorable. All right, that's for Bronsted. And now we come to Lewis. Lewis is the most comprehensive definition of what an acid and base is. Although we need to do more Bronsted acid-base reactions. Let's do one more example of a Bronsted acid-base reaction before we leave it. Lewis. Actually, we're going to come back to it. We'll come back to it after this. Well, Lewis acid base, CO2 I told you is an acid, but it's not a Bronsted acid. CO2 is what we call a Lewis acid. What Lewis acids are capable of doing is they're capable of accepting electron pair. Lewis bases are electron pair donors. And so ammonia is electron pair donor, the electron pair. The electron pair can pick up the proton and form similar to ammonia. But BF3 here, BF3 doesn't look like an acid because there's no H. But you don't need H. Just BF3 just has to accept the proton pair. Electron pair. And so what happens is this native boron's positively charged here because of attraction here. This boron's missing an octet. It can get its octet if this lone pair is shared. Well, fluorine doesn't want to share another lone pair, so fluorine won't donate another lone pair to the bond. Do you remember me talking about this? What did I say about fluorine? Does fluorine ever form double bonds? Why not? doesn't, but boron would like it to form a double bond. We talked about BF3 specifically. You have BF3 in your notes? Well, I was thinking about asking this question as a multiple choice question in the last test. Good thing I didn't. Because maybe nobody would have gotten it. Or maybe you would have guessed it. Probably would have guessed it. Who knows? But in BF3, fluorine would not form a double bond. You know, we'd like to complete the octet of boron. Take a lone pair off fluorine. There are 3 lone pairs here. Just take one of the 3 lone pairs here and make a double bond, then we got an octet. Everybody's happy, right? Everybody would be happy if everybody had an octet.
But, if fluorine took one of its pairs,
Uh-huh.
lend that electron, or it wouldn't lend both of the electrons, it would lend the one to Carl. So wouldn't it have like an extra electron that's not in a bond, and it's now an empty pair?
No, the whole pair would come down. I'll show you the quick resolution to fix the structure. If I drew it like this is how I drew it. You just take one of the lone pairs. I don't know why. This drives me crazy. What drives me crazy is they didn't bother to put the lone pairs on the fluorine. That drives me crazy. I don't see the lone pairs on fluorine. I think it's wrong not to draw the lone pairs on fluorine. You need to do that. If we just took the 3 lone pairs, if we just pick one of the fluorines, we've got 3 resonance forms for this, right? Because we could pick one or 3. If we got 3 resonance forms, we'd have a resonance hybrid. But it doesn't do this. Why doesn't it do this? What was the reason it didn't do this? It should, because, boron ends up short an octet. And so we end up with this structure where fluorine has the octet. Just trigonoplanar, by the way. Fluorine has octet, so we can easily get boron to have an octet by just taking a lone pair and bringing it in here. Lone pair bringing it here, and a double bond. Everybody has an octet. Everybody has an octet. Everybody's happy, right?
Formal charge.
Formal charge.
Yeah. So fluorine never forms double bonds because in order to form a double bond, what has to happen? I don't know. I think I spent like 10 minutes talking about this earlier, but it doesn't register. That 10 minutes is just. Well, you don't need. You could just figure out the formal charges. What are the formal charges? You're right. It is the formal charges, so you probably would have gotten it right on the test. What are the formal charges?
Fluorine should be -1, but with the double bond, it's.
No, redo the formal charges. Do the formal charges on this structure first. This is the structure of BF3. This is not the structure of BF3. Boron's unhappy in this structure. Boron's unhappy because it has less than an octet. That's not good. So normally in Lewis structures, when we draw Lewis structures, this is the first thing we try to do. We try to get octets on everybody. But I told you about fluorine though. But what's the formal charge on boron? Also practice, the more practice you can do, and the more practice, maybe, Newton's not enough practice, or the thing is not enough, so you can do some of the problems in the book. The answers are there for the blue problems. The answers in the back of the book. Well, formal charge, we assume the bonds are 100% covalent or 100% ionic? Covalent. What does that mean? So what that means is, rather than having this 100% covalent fancy language, I just call it what? These are my words. I call it 50-50, which means what?
On split.
Yeah, they split. Just split. So boron ends up with 1, 2, 3. See, I do these little words to help me remember things like 50-50, winner takes all, this kind of thing. But maybe those don't register for you. So you want to think of your own, words. You think of your own words, it's way better. Eventually you want to do things in your own words. But, so boron ends up with 3. How many is it supposed to have? It's supposed to have, how many valence electrons? I'll do it for let me bring up the periodic table here. All right, so how many valence electrons is boron supposed to have? Just right here. 3. 3. Carbon has 4. Nitrogen has 5. Oxygen 6. Fluorine 7. Neon 8. Just on 10. So boron's supposed to have 3. Well, it has 3, so the formal charge is 0. Fluorine's? No, it has 7 because remember 50-50. And so 2, 4, 6, 7. It's supposed to have 7. It has 7. That's fine. So everything's evenly distributed. What they put in is what they got out. That's what formal charge is. How about this structure above?
That one it only had 4 only have 6.
It only has 6. So fluorine put in 7, but it only got 6. This is like what they say about, the federal taxes. California pays a lot in federal taxes, but what they get back from the government, federal government, is much less, So you put in 7, you get 6 back. Are you happy? No. So you put in 6, you put in 7, you get 6 back. You're in the deficit. Boron's very happy because boron put in 3, and how many did you get back? 4, which means. Does that look good? Boron takes an electron from fluorine. You think that'd ever happen?
No.
And so this is why fluorine, in order for fluorine to double bond, it's going to lose some of its charge. It loses its electrons. It's going to sharing in the act of sharing. Just fluorine. Chlorine's okay, Chlorine could get a double bond, perhaps. That's a little bigger, so it's not. That's electron hungry. There's fluorine. Fluorine's very electron hungry. And so, going back to this is, so boron can't get it from fluorine. Boron has to seek that extra electron from somebody else. Well, what might be willing to sacrifice? Fluorine for sure not, but what about nitrogen? Yeah, nitrogen will. And so this happens, but when nitrogen does this, what happens to the charge on nitrogen? Nitrogen here, what's the formal charge on it? It has 5, and how many did it contribute? In the structure it has 5, or did it contribute 5? Well, it contributed 5 because it has 5 valence electrons. In the structure, did it get back 5 electrons, or more or less? It got back 5, so the formal charge is 0. Take a look at the second structure. The nitrogen, it lost 1. That's positive. But that's okay for nitrogen. A positive charge on nitrogen is okay. A positive charge on fluorine is unacceptable because fluorine is the most electronegative element on the chart. And so in this case, nitrogen is going to end up with a positive, boron's going to end up with a negative. But this happens because now boron has an octet. Now it's finally happy because it was unhappy before. But it's going to get an octet from nitrogen. It couldn't get an octet from fluorine. This is an example of a Lewis acid-base reaction here. This is the type of reaction that happens. You know, we talk about the decomposition of carbonic acid. Carbonic acid is very unstable. What does it decompose into? CO2 and water. That is a Lewis acid base decomposition. It's not a redox decomposition. And so, you know, we all know carbonic acid is totally unstable. It's going to decompose into H2O liquid plus CO2 gas. This is Lewis acid base. The oxidation states don't change. That's how you know. You know, some decompositions are redox, some decompositions are Lewis acid base or acid base. This is why I don't like to classify decomposition reactions as decomposition and put all decomposition reactions in the same category, because not all decomposition reactions are alike. Yeah. Well, this is how this particular reaction works. Let's look at the reverse reaction. If we look at the reverse reaction, we got CO2. CO2 has this Lewis structure. Is this polar or non-polar, this molecule? Polar? So CO2 and water like each other. CO2 is polar, water is polar. They like each other, and so CO2 dissolves in water easily and to a large extent. No. You can force CO2 in water. How do you force CO2 in water? You give it lots of pressure. 1 atmosphere of pure CO2, you know. That's a lot of pressure compared to air. You know, air is only 0.0003 atmospheres CO2. CO2 is non-polar, but these bonds are highly polar. How come it's non-polar with polar bonds? Like, for example, this bond is very polar. If you drew the dipole, which is this arrow, you have an arrow pointed towards oxygen because oxygen is more electronegative, leaving carbon positive. And so these bonds are highly polar, but this molecule is non-polar because, yeah, equal and opposite. And so there's no net. But what it does mean is that it means that the carbon is positive and the oxygens are negative. And so we do have some charge there. Well, if you're water, you're attracted to both because water can go either way, right? And so one end of water will be attracted to the positive, the other end of the water will be attracted to the negative. So if you're water, you can go both ways. Well, what happens here is if there's a violent collision, this water hits the carbon. But carbon, can it have more than an octet? No, carbon cannot have more than an octet. You'll learn this in Chem 1A. The maximum for carbon and nitrogen is just an octet. Some atoms can have more. And so what happens is this lone pair comes in here, it's got to knock the lone pair out. or not a lone pair, but a bonding pair out. Otherwise, carbon can't maintain its octet. And so we have some kind of violent collision like this, resulting in some kind of reaction that occurs here. And so we end up with a structure like this, where now this oxygen has a single bond and 3 lone pairs, giving it a negative charge here. This oxygen is still double bonded with 2 lone pairs, 0 charge. Now we have this thing here coming in like this. We've seen something like this before, where oxygen has 3 bonds and a single lone pair. What's the charge on this oxygen here? The formal charge.
Which one?
This one.
0. No.
This one's 0. This one doesn't have a 0 formal charge.
Which the oxygen so we have minus.
This one has a minus
Plus
1 charge. Is this one minus 1 also?
no. Plus 1.
It's plus 1. This one's plus 1. Is that stable?
No.
No, so this one can fall apart back, but something interesting can happen. What's interesting that can happen is this. We call this, inter versus intra. Inter means what? Intra means what?
Intramolecular, or intra is between the components of the molecule, and then inter are between the molecules.
Right. Intra is within the molecule. Inter is between 2 different molecules. And so this is what we call an intermolecular proton transfer. That is, a proton was transferred from one molecule to the other. This is what we call an intramolecular proton transfer. What's going to happen is this vibration, and this oxygen can come over here. This oxygen is going to be very attracted to this hydrogen. And so this oxygen, if there's a vibration, can pluck off that hydrogen and leave the electrons here. If that oxygen comes in and plucks the hydrogen here, then what do we end up with? We end up with this molecule. This. And that lone pair stays there because it just takes the hydrogen. Do you recognize that molecule? What's the formula for that molecule? The molecular formula for that molecule? How many hydrogens do we have?
Plus 2.
So that'd be H2, and the H's are bonded to oxygen. So those are probably acidic hydrogens. H2CO3. 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 So we have CO2 plus water yields H2CO3. Well, H2CO3 is not that stable, but like I said before, we could either say no reaction or a little bit of reaction occurs. In this case, a little bit of reaction occurs. And so if you bubble CO2 in water, you're going to form a little bit of carbonic acid, but mostly it's going to be CO2 in water. Does that make sense? It's like ammonia in water. It's mostly ammonia in water, but a little bit of ammonium and hydroxide. And so this is the same type of deal. And this is same type of deal. Yeah. And so this is another example of Lewis acid base. Lewis acid base. You see how much more complex Lewis acid base reactions are. Lewis acid base reactions. What we do is we do this. We look at how the electron pairs go. So this electron pair is going to push into boron here, and then we're done. So I draw a little arrow here, heat arrow, like this. It's a reaction. This boron's positive, the fluorines are negative. This this nitrogen is negative. Positive, negative, they like each other. Reaction occurs. Yeah. Same.
And so Lewis acid base are a lot more difficult than Bronsted acid base. And so this is why we spent all our time on Bronsted. Arrhenius is very easy. H plus and OH minus, only one reaction, so you're not going to waste too much time for Arrhenius. So we spent most of our time on Bronsted, but we didn't have to spend any time on Bronsted because all acid-base reactions fall under the category of Lewis. It's just, if we place everything under Lewis, then we have to do this kind of deal for everything. It's too much work. And so it's much easier to do Bronsted as just the proton being transferred rather than looking at how these electron pairs. You see what I'm doing with the electron pairs? Moving them about. That's what we do with Lewis. And so Lewis is what we call the global definition. And in that global definition, we have little sub-definitions that we're looking at. And so when we have the Earth, then we'll have different continents. And so Bronsted Lowry would be a continent, but everything falls under Earth, so that would be Lewis. Then we have this. We already talked about conjugate acids and bases. When we look at reactions, it's always a competition. This is why we're always going stronger to weaker. You know, we want the weaker side to be the products, because if the weaker side's the products, it's more stable energetically. And so it's a competition. We're always looking at, you know, what would the product combination do compared to the reactant combination. And so this is what we talk about conjugates here, because if we have a base here, and the base accepts a proton, then it turns into an acid. And if we have an acid, acid loses a proton, it turns into a base. And so these are the conjugate pairs. It's like, this is why we only need one chart. Just like, you know, the conjugates for this. I already talked about conjugates. First time we saw conjugates was here. Fluorine, this isn't the greatest resolution here. Fluorine is an oxidizer or reducer? Oxidizer. That means fluoride is its conjugate reducer. So we only need one chart, you know? If this is the way it works. We have the conjugate relationship. The conjugate relationship always works this way. If one side's powerful, the other side must be weak. Because if fluorine really wants electrons, once it gets those electrons, is it going to let them go? No. So the opposite reaction is not favorable. The forward reaction is strongly favorable. The same conjugate relationship happens with acids and bases. And so we only need one chart here. So if the acid is strong, a strong acid means it doesn't want that proton, it donates it easily. That means its conjugate base here is going to be very weak, because why would it want a proton if the acid gave up the proton so easily? And so this is why there's a conjugate relationship. Strong acid, weak base. Weak acid, strong base. Weak acid means it wants to hold on to that hydrogen. It wants to hold on to that hydrogen, it's not going to let it go. And so at the opposite end of the chart, is methane going to lose that? We talked about methane. I told you methane's not an acid. It isn't. You know, we don't consider it unless you have a super base. If you have a super base, then it might be able to pluck off the hydrogen, but we don't really deal with super bases. And so methane, let's say you want to neutralize some base, don't use methane. It's not really going to work. But if something were to pluck off a proton off methane, then you'd form an extremely powerful base, methide. Methide is incredibly reactive and dangerous base. Same thing with hydrogen. Is hydrogen good at neutralizing base? You don't think of hydrogen as consisting of H plus and H minus, right? So that means hydride is powerful. Hydroxide, normally we don't even consider hydroxide as an acid. But here it's an acid. Why is it an acid? Because it can lose a hydrogen. If hydroxide loses a hydrogen, it forms oxide. Oxide is a powerful base.
And so we have the conjugate relationship. That's what this is showing. Is this a favorable reaction? Well, you know what we say, weak acids partially hydrolyze or partially ionize in water. This is hydrolysis because we're forming hydronium instead. And so weak acids partially, they partially because this is not a favorable reaction. We're going, acetic acid, which is the acid, plus the base, which is water here, is going to yield hydronium plus acetate. In other words, hydrogen ions and acetate. It's a weak acid. Weak acids only partially react because we're going from acetic acid to hydronium. Well, which one's stronger, acetic acid or hydronium? Well, acetic acid is written a little differently here, but here's hydronium. Hydronium is the strongest acid that can exist in water. That's why you see these two bars here. Hydronium is the strongest acid that can exist in water. Therefore, any acid that's stronger cannot exist in water. And so all these are going to hydrolyze or ionize 100% in water. These can exist in water. These are the weaker ones. So where's acetic acid? Here's acetic acid. Acetic acid is written CH3COOH or HC2H3O2. Acetic acid is hydronium. So acetic is weaker. So when we look at this reaction, we'd say there's no reaction, right? Normally we just say no reaction, but there's no driving force. No driving force, no reaction. And that's accurate if there's a huge difference, If one side is extremely lopsided. If it's extremely lopsided, then we expect no reaction. So let's say the products were much, much stronger than the reactants, then it'd be totally lopsided, and so with no reaction. It's such an uphill. But if there isn't a huge difference, then we might have a little bit of reaction because not all acetic acid molecules, not all water molecules will have the same energy. We have a distribution of energies. Do you remember the energy distribution curve when we were talking about vapor pressure? You guys remember that? That was 15. Remember this curve? This is like say water molecules at 25 degrees C. This is what we used it for. Water molecules at 25 degrees C, there's a small fraction of water molecules that has enough energy to escape, right? Well, if there's not a huge difference here, there's a small fraction of molecules which have enough energy to react. If there's a huge difference here, then there aren't enough molecules that have enough energy to overcome this barrier, what we're saying. And so, we come back to this. And so even though there's no driving force, because we're going from a weaker acid to a stronger acid. If we're going from a weaker acid to a stronger acid, we say no driving force, therefore no reaction, right? But then we look at how big of a difference is it. Is it a huge difference? If it's an enormous difference, then for sure no reaction. We don't expect anything to happen. But if it's not huge, then you get more and more reaction, right? And eventually, once it flips to the other side, then we can expect reaction to occur.
And so what happens is about 1%, less than 1% of the molecules here can react. Less than 1% have enough energy to collide to break the bonds in this fashion. This is why, do you see the double-headed arrow? This is not a double-headed arrow. Do you remember the double-headed arrow? The double-headed arrow is a single line with two arrowheads on it. This is the double-headed arrow. This is different. This is one forward arrow and one reverse arrow. What was the double-headed arrow used for?
That was like showing random structure.
Yeah, showing the covalent resonance forms. This is used to show something else. This is used to show that both reactions can occur. But when you look at this, it appears that both reactions occur to the same extent. They don't. Which one is favored? The reverse or the forward?
The reverse.
The reverse. So sometimes what we'll do is we'll draw a gigantic reverse and a tiny forward. That's just to show which side's favored. Sometimes they draw the arrows equal sides because the rates of reaction are the same. You reach the state of dynamic equilibrium. All right, let's try some conjugates here. What is the conjugate acid of ammonia? So ammonia is a base, and bases accept protons, so it accepts an H+. And so when NH3 accepts an H+, what forms? NH4+. And so that would be the conjugate acid of NH3, NH4+. What is the conjugate acid and the conjugate base of bicarbonate? Bicarbonate's amphoteric, so it can go either way. And so these conjugates, this is the way we do the conjugates, or you just look it up on the chart. And so ammonia is what we call a base in this case. So that's a base, then it accepts a proton to form ammonium. So this would be the acid. Okay, bicarbonate can go either way. Bicarbonate can be the acid. If it's the acid, then it donates a proton. If it donates a proton, it's going to form H+ and carbonate. If it's a base, then bicarbonate accepts a proton to form H2CO3. And so if it's an acid, then this must be the base. If this is the base, this must be the acid. And so those are the conjugates. Yeah. So, that's how we do it. Figure it out. Those are conjugate pairs, acid-base pairs. The conjugate pairs are shown in the acid-base chart. All these are conjugate acid-base. So the acids are on the left, bases on the right. But some species, like bicarbonate, occur on both sides. So let's take a look at bicarbonate quickly. And so here's bicarbonate. Is bicarbonate acting as the acid or is it acting as a base? It's on the left side. So it's the acid. So this must be its conjugate base. Here bicarbonate is again, but this is bicarbonate acting as the base. And therefore, carbonic acid is unstable. Carbonic acid decomposes into CO2 and water. So that would be its conjugate acid. Here's a conjugate relationship. Well, this is a mix. There are a couple of things. Two things on this slide. One is electrolyte properties. Strong acids are strong electrolytes. Strong electrolytes ionize completely or hydrolyze completely. So strong acid hydrolyzes or ionizes completely. Strong bases hydrolyze or ionize completely. Well, strong bases don't ionize. Strong bases hydrolyze. I don't know why it's not parallel. This is weird. Weak acid, weakly ionized. So strong bases hydrolyze completely. Weak bases partially hydrolyze. Okay, so that's point 1. So this slide is screwed up. Point 2 is reactivity. You know, as far as reactivity goes, strong acids are good proton donors. Strong bases are good proton acceptors. They're good at extracting protons. That's point 2. Point 3 of this slide, there are 3 points on this slide, and it's not clear. Point 3 is the conjugate relationship. If it's strong on one side, it's going to be weak on the opposite. That's it. And so this is point 2. Strong acid, weak conjugate base. Weak acid, strong conjugate base, or stronger conjugate base, because acetate's not strong base. Acetate's still weak base. So we should say stronger, weaker. And so this is why I don't say strong and weak. I just say stronger, weaker. So 3 points on the slide, but those 3 points I've already talked about. So here's the acid-base chart from your book. It's pretty much the same as ours, you know, pretty much, except we have more bases. So let's take a look at their chart then. At the top of their chart is HI. You remember what was at the top of our chart? HClO4. So our chart and then their chart don't exactly agree, because HClO4 is number 3 here. But you know, it's a very small difference, perhaps. It depends on who measured it and what time it was measured. But anyway, we have the 7 common strong acids here. 1, 2, 3, 4, 5, 6, 7. These have 7 common strong acids people memorize. And then if they encounter an acid they've never seen before, have you ever seen this acid before? HC7H5O2? You've never seen, well, you've probably seen that acid before, because do you know what the name of that acid is?
No.
Well, let's take a look and see if we can find the name of this acid. HC7H5O2. So let's just search it here. It was HC7H5O2. Let's find out the identity of that acid. Identity of that acid is benzoic acid. Benzoic acid. I guess I didn't have to do that because it's on the chart here. I would have just scrolled over a little bit. Benzoic acid is a common name. What other ones do we have? There's some different ones here, and a lot of the same. Hydrocyanic acid is not on our chart. You can see, and it's a pretty weak acid, hydrocyanic acid. Hydrocyanic acid is very dangerous because of its acid strength. Not a very strong acid. Hydrocyanic acid is one of the most feared acids. You know, there are a number of very feared acids. HCN's one because it's easy to form. HCN's one because if you take any cyanide salt and add acid to it, you know, like sodium cyanide or potassium cyanide, and add acid to it. In fact, I think I read this not too long ago. What was it? There's one of these things in these gas chamber type salts.
You take the salt, sodium cyanide, and add acid to it. This is a metathesis reaction. So sodium cyanide plus something like HCl or some other acid will form what?
Would it just be sodium chloride and then
Yeah, sodium chloride and
hydrogen, or cyanic acid?
yeah, hydrocyanic acid or HCN. HCN is aqueous or gas depending on the temperature and how much is generated. Even though it's fairly polar, you expect it to be pretty soluble. And so we're going from stronger acid to weaker acid, stronger acid to weaker acid is the driving force, and then gas formation. But HCN gas, so any acid added to any cyanide salt will generate HCN. HCN is very feared because HCN, if you breathe in the stuff, and this is they use I guess it smells like bitter almonds. The smell of it, or the taste of it, you know, is used.
So if it's so weak, why is it so weird? Like it's such a weak acid, why?
Well,
is it-
because cyanide, you know, even cyanide tablets are, you know, I don't know if this is accurate, but, you know, people would carry cyanide capsules, you know, the cyanide capsules for suicide. Have you heard of that thing? Or HCN for gas chambers, capital punishment, that kind of thing. And so the cyanide is very dangerous itself. It's not because it's a strong acid, it's because of the cyanide. What about the cyanide? Well, it turns out that cyanide is a powerful Lewis base. It's not a very powerful Bronsted base, but it's a powerful Lewis base. As far as Bronsted bases go, you know, you can see it on the chart here. It's pretty weak. I mean, it's like carbonate. But, you know, do you worry about carbonate poisoning? Like if you're chewing on a piece of rock, like limestone, I wouldn't worry about dying. But if you're chewing on a piece of sodium cyanide, I wouldn't worry about dying. I would worry about dying because of this. Cyanide's a Lewis acid, and then heme. This is our Lewis base. This is Lewis acid. And so we have a Lewis acid base reaction occurring. So let's just take a quick peek at that. Cyanide poisoning. Cyanide poisoning results in exposure to cyanide. This is the cyanide ion, carbon and nitrogen. Let's look at well, there's an antidote. What's the antidote? ML nitrate. Well, let's take a look at the mechanism. What we want to see is, you know, how does it work? So let's look at the cyanide.
especially occurring in cassava. We see cyanide in spy movies as the typical or classic pill the spy takes to commit suicide so he doesn't have to divulge any of his secrets. And cyanide has also been labeled as vitamin B17 or latrile, which is touted as a secret cure for cancer that the FDA doesn't want you to know about. Here we see the mechanism of action of cyanide attaching to the cytochrome oxidase molecule. And again, cytochrome oxidase is the final enzyme in the electron transport chain that's responsible for oxidative phosphorylation. Cyanide is described to have an odor of bitter almonds if one were to smell it. And the classic scenario for cyanide poisoning involves a firefighter that enters into a household that's on fire but without wearing any protective respiratory gear. Firefighter enters into the household where household products have been on fire, including insulation in the house, perhaps some rubber or polyurethane, construction or building materials or furniture, and he or she inhales that gas, exits the house, feels a sensation of shortness of breath, dizziness, confusion, ataxia, chest pain, and then collapses. In those settings, the treatment for cyanide poisoning should begin immediately. Overall signs and symptoms of cyanide poisoning.
Okay, let's look at the mechanism. a little bit
Or
more.
cyanide within the body.
Basically, cyanide, is it a strong acid? No. Is it a strong oxidizer? No. And what type of reaction is it? Well, it's an acid base, but it's not a Bronsted acid base. It's not a metathesis reaction. Well, in certain respects, it might be considered metathesis, but
It's a Lewis acid base reaction. And we could look at the structure in more detail, but
we'll just leave it at the question. We'll just go on. And so this is why we when we're thinking about, acid properties or whatever else, this is why I like to categorize it in different categories. Looking at the different ways things can react. And so HCN seems very unreactive but it isn't. You got to worry about other types of reactions here. All right, so this is the acid-base chart. We're looking at the conjugate relationship earlier. So let's continue with this. So list the following acids according to strength, decreasing strength.
well, just take a guess. Which one of these do you expect to be the strongest? Phosphoric acid, ammonium ions, or the hydrogen oxalate? Bioxalate.
Just take a guess. Without looking, what do you think would be the strongest? Phosphoric acid, that's correct. Between ammonium and hydrogen oxalate, this is more tricky. I wouldn't expect you to know that one. That one we just consult the chart. So here you just consult the chart. Turns out in figure 17.6, this is the ordering. Predicting acid-base reaction. Acid-base reactions can be predicted on the relative strengths of the conjugate acid-base pairs. Stronger acids and bases are the most reactive. Weaker acids and bases are the most stable and less reactive. Stronger acid will always surrender a proton to the stronger base, yielding the weaker. If there's a driving force. That is, if only there's a driving force. And so this is the diagrammatic scheme here. We want to go from stronger to weaker. Stronger acid to weaker acid. We want to go from stronger base to weaker base. But this scheme confuses me. So I'm going to skip it. Steps to predict. Well, these are basically the steps we've already done with a very wordy way of saying it. And so we're going to do a Bronsted acid-base reaction now. Do the Bronsted acid-base reaction between hydrofluoric acid and sulfide ion. Predict which side will be favored. In other words, predict the favored side is the weaker side. So predict which side will be favored.
hydrofluoric acid and sulfide. So the reaction here would be like hydrofluoric acid. Hydrofluoric acid is also a very feared acid. Is it feared because of its acid strength? No. Hydrofluoric and hydrocyanic acid are the two of the most feared. They're two acids. Both are weak acids, and both people don't like. They don't want to be around them. They don't want to work, and especially they don't want to work anywhere where they might be generated. So hydrofluoric is HF. And sulfide. What's the formula for sulfide? SO3 charge. So this would be like this. We might take HF and sodium sulfide. When you look at that, hey, that looks like what type of reaction? This is why they didn't write it like this. They didn't write it like this because they didn't want to confuse you, because automatically you'd see this and you'd go, hey, that's a AB plus CD double replacement reaction. So the reason they didn't put sodium there is so you wouldn't be fooled into doing a double replacement reaction, which you automatically would have done had you seen that. And so this is one way to avoid having to talk about, you know, the possibility of a double replacement reaction going, because if they write it like this, HF plus sulfide, then this to me also looks like metathesis, you know, it's ion combination, it's ions. But automatically people go AB plus CD yields what? AC plus, yeah. And so we could do that. Well, it would have been okay to do that here as well, but we're doing it slightly different. For Bronsted, we make a prediction. I don't know if anybody remembers, but for Bronsted, how many protons do we transfer at a time? One. For double replacement, what do we do? For double replacement, we go all the way. And so this is what I would have done in double replacement. In double replacement, I would have gone to H2SO4 plus sodium fluoride. H2SO3. H2SO3. That is, you know, I have hydrogen ions and sulfide. Well, hydrogen ions and sulfide makes H2SO3, and then I have sodium ions and fluoride ions, which makes sodium fluoride, and then balance everything. I get 2 here, 2 here, and then it's balanced. For Bronsted, we only transfer 1 proton at a time, and so this makes a different product. In this case, what we're going to form is fluoride and HSO3 minus. And so these are 2 ways of handling kind of the same type of reaction. This is the Bronsted. This is the metathesis. And so metathesis, we just assume complete reaction. For Bronsted, we just do it 1 step at a time. And so do you see here, they do it 1 step at a time. We don't, even though sulfide is what we call a dibasic base, it could take 2 protons. And so we just transfer 1 proton at a time. Then we look at which side's favored. So which side's favored here? Well, we need the chart for that. I don't expect you to have it memorized. So we go to the chart, and we're comparing HF with HSO3 minus. In fact, I don't have HSO3 minus on my chart. My chart is not as good as their chart. We should use their chart, which is better. So here's HSO3 minus. HF. HSO3 minus. HF is up here. So we're going from stronger HF to weaker HSO3 minus. Now, if I went all the way here, look at the top reaction, HF versus H2SO3. HF versus H2SO3, if I went all the way, then H2SO3 is up here, HF is down here, which tells me that there should be no reaction. And so metathesis, the reason we're gonna go all the way is just to keep things simpler. In reality, it happens one step at a time, but I don't wanna get into the complexities of doing it one step at a time. And so I'm trying to keep it simpler but it's not always the most accurate way of doing it, but it's okay, because most of the reactions will go all the way. And then I did throw in a front step.
We're at time.